Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young. Section 2, Consistency, Categoricalness, Independence. Example of a mathematical science. The notion of a class of objects is fundamental in logic, and therefore in any mathematical science. Note, synonyms for class are set, aggregate, assemblage, or totality. The objects which make up the class are called the elements of the class. The notion of a class, moreover, and the relation of belonging to a class, being included in a class, being an element of a class, etc., are primitive notions of logic, the meaning of which is not here called in question. The development of the preceding section may now be illustrated and other important conceptions introduced by considering a simple example of a mathematical science. To this end, let S be a class, the elements of which we will denote by A, B, C, etc. Further, let there be certain undefined subclasses of S, any one of which we will call an M class. Concerning the elements of S and the M classes, we now make the following assumptions. 1. If A and B are distinct elements of S, there is at least one M class containing both A and B. 2. If A and B are distinct elements of S, there is not more than one M class containing both A and B. 3. Any two M classes have at least one element of S in common. 4. There exists at least one M class. 5. Every M class contains at least three elements of S. 6. All the elements of S do not belong to the same M class. 7. No M class contains more than three elements of S. The reader will observe in this set of assumptions we have just two undefined terms, namely element of S and M class, and one undefined relation belonging to a class. The undefined terms, moreover, are entirely devoid of content except such as implied in the assumptions. Now the first question to ask regarding a set of assumptions is, are they logically consistent? In the example above of a set of assumptions, the reader will find that the assumptions are all true statements if the class S is interpreted to mean the digits 0, 1, 2, 3, 4, 5, 6, and the M classes to mean the columns in the following table. Table 1, by column, 0, 1, 3, 1, 2, 4, 2, 3, 5, 3, 4, 6, 4, 5, 0, 5, 6, 1, 6, 0, 2. This interpretation is a concrete representation of our assumptions. Every proposition derived from the assumptions must be true of this system of triples. Hence, none of the assumptions can be logically inconsistent with the rest. Otherwise, contradictory statements would be true of this system of triples. Thus, in general, a set of assumptions is said to be consistent if a single concrete representation of the assumption can be given. Note, it will be noted that this test for the consistency of a set of assumptions merely shifts the difficulty from one domain to another. It is, however, at present the only test known. Knowing our assumptions to be consistent, we may proceed to derive some of the theorems of the mathematical science of which they are the basis. Any two distinct elements of S determine one and only one M class containing both these elements, by assumptions 1 and 2. The M class containing the elements A and B may conveniently be noted by the symbol AB. Any two M classes have one and only one element of S in common, by assumptions 2 and 3. There exist three elements of S, which are not all in the same M class, by assumptions 4, 5, and 6. In accordance with the last theorem, let A, B, C be three elements of S not in the same M class. By assumption 5, there must be a third element in each of the M classes AB, BC, CA, and by assumption 2, these elements must be distinct from each other and from A, B, and C. Let the new elements be D, E, G, so that each of the triples ABD, BCE, CAG belongs to the same M class. By assumption 3, the M classes AE and BG which are distinct from all the M classes thus far obtained, have an element of S in common, which, by assumption 2, is distinct from those hitherto mentioned. Let it be noted by F, so that each of the triples A, E, F, and B, F, G belong to the same M class. No use has yet been made of assumption 7. We have then the theorem, any class S subject to assumptions 1 through 6 contains at least 7 elements. Now, making use of assumption 7, we find that the M classes thus far obtained contain only the elements mentioned. The M classes CD and AEF have an element in common by assumption 3, which cannot be A or E, and must therefore, by assumption 7, be F. Similarly, ACG and the M class DE have the element G in common. The 7 elements A, B, C, D, E, F, G have now been arranged into M classes according to the table. Table 1', read by columns, A, B, D, B, C, E, C, D, F, D, E, G, E, F, A, F, G, B, G, A, C, in which the columns denote M classes. The reader may note at once that this table is, except for the substitution of letters for digits, entirely equivalent to Table 1. Indeed, Table 1' is obtained from Table 1 by replacing 0 by A, 1 by B, 2 by C, etc. We can now show furthermore that S can contain no other element than A, B, C, D, E, F, G. For suppose there were another element T. Then, by assumption 3, the M classes TA and BFG would have an element in common. This element cannot be B, for then ABTD would belong to the same M class. It cannot be F, for then AFTE would all belong to the same M class. And it cannot be G, for then AGTC would all belong to the same M class. These 3 possibilities all contradict assumption 7. Hence, the existence of T would imply the existence of 4 elements in the M class BFG, which is likewise contrary to assumption 7. The properties of the class S and its M class may also be represented vividly by the accompanying figure, Figure 1. Here we have represented the elements of S by points or spots in a plane, and have joined by a line every triple of these points which form an M class. It is seen that the points may be so chosen that all but one of these lines is a straight line. This suggests at once a similarity to ordinary geometry. Suppose we interpret the elements of S to be the points of a plane, and interpret the M classes to be the straight lines in the plane, and let us reread our assumptions with this interpretation. Assumption 7 is false, but all the others are true, with the exception of assumption 3, which is also true except when the lines are parallel. How this exception can be removed will be discussed in the next section, so that we may also regard the ordinary plane geometry as a representation of the assumptions 1 through 6. Returning to our miniature mathematical science of triples, we are now in a position to answer another important question. To what extent do assumptions 1 through 7 characterize the class S and the M classes? We have just seen that any class S satisfying these assumptions may be represented by table 1' merely by properly labeling the elements of S. In other words, if S1 and S2 are 2 classes S subject to these assumptions, every element of S1 may be made to correspond to a unique element of S2 in such a way that every element of S2 is correspondent to a unique element of S1. And that to every M class of S1 there corresponds an M class of S2. The 2 classes are then said to be in 1-to-1 reciprocal correspondence, or to be simply isomorphic. Two classes S are then abstractly equivalent, i.e., there exists essentially only one class S satisfying assumptions 1 through 7. And this leads to the following fundamental notion. A set of assumptions is said to be categorical if there is essentially only one system for which the assumptions are valid, i.e., if any two such systems may be made simply isomorphic. We have just seen that the set of assumptions 1 through 7 is categorical. If, however, assumption 7 be omitted, the remaining set of 6 assumptions is not categorical. We have already observed the possibility of satisfying assumptions 1 through 6 by ordinary plane geometry. Since assumption 3, however, occupies as yet a doubtful position in this interpretation, we give another, which by virtue of its simplicity is peculiarly adapted to make clear the distinction between categorical and non-categorical. The reader will find, namely, that each of the 6 assumptions is satisfied by interpreting the class S to consist of the digits 0, 1, 2, 12, arranged according to the following table of M classes, every column constituting one M class. Table 2, read by columns, 0, 1, 3, 9, 1, 2, 4, 10, 2, 3, 5, 11, 3, 4, 6, 12, 4, 5, 7, 0, 5, 6, 8, 1, 6, 7, 9, 2, 7, 8, 10, 3, 8, 9, 11, 4, 9, 10, 12, 5, 10, 11, 0, 6, 11, 12, 1, 7, 12, 0, 2, 8. Hence, assumptions 1 through 6 are not sufficient to characterize completely the class S, for it is evident that systems 1 and systems 2 cannot be made isomorphic. On the other hand, it should be noted that all theorems derivable from assumptions 1 through 6 are valid in both systems 1 and 2. These two systems are two essentially different concrete representations of the same mathematical science. This brings us to a third question regarding our assumptions. Are they independent? That is, can any one of them be derived as a logical consequence of the others? Table 2 is an example which shows that assumption 7 is independent of the others, because it shows that they can all be true of a system in which assumption 7 is false. Again, if the S class is taken to mean the three letters A, B, C, and the M classes to consist of the pairs A, B, B, C, C, A, then it is clear that assumptions 1, 2, 3, 4, 6, 7 are true of this class S, and therefore that any logical consequence of them is true with this interpretation. Assumption 5, however, is false for this class and cannot, therefore, be a logical consequence of the other assumptions. In a like manner, other examples can be constructed to show that each of the assumptions 1 through 7 is independent of the remaining ones. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.